Good morning. It's 7:05 on a Thursday. I'm going to have to teach a lab at 9:30, but I'm an amazing teacher, so I am going to make this recording right now for you. So, okay, acids and bases, we know already if we have a weak acid, for example, nitrous acid, HNO2, that this is weak. We can look this up. If we don't find it on a table, then we know it's weak. It breaks apart into hydronium or reacts with water to form hydronium ions and NO2 minus nitrite, right? So not nitrate, but nitrite. Anyway, you should know that this reacts with water, obviously, to form hydronium. And then that is the constant. That is the actual species that is in water that we measure to determine the pH. Okay, so we've also understood that this right here is the conjugate base. So we know it can react with water in an equilibrium reaction that forms a little bit of that nitrous acid back, HNO2, and then produces some hydroxide, which makes a solution that has a source of nitrite in it basic. Alright, so well, it could be a source of nitrite, right? Well, those are going to be salts because those are polyatomic ions. So it could be sodium nitrite or calcium nitrite, you know. So then we need two of those, right? So there you will have to be able to recognize which one of these salts will produce acids or bases in solution, and sometimes the cation can also react with water. Now, in the case of sodium would have to react with water to form sodium hydroxide, and sodium hydroxide for it to be an acid, right, would have to produce sodium hydroxide, and we know sodium hydroxide is a very strong base, so that's just going to be neutral, right? But you might have to look at some of these ions here and then decide if they're either acidic or basic in solution. So nitrate here, and HNO3 comes from nitric acid, HNO3. It is not weak, and so it's going to be neutral, right? It's going to be a pH neutral ion. Nitrite, we already established, is going to have a basic solution or a pH of larger than 7, and then acetate is the conjugate base of acidic acid, which is weak, so it will also produce a weak, or it will act as a weak base because it is a conjugate base of that, all right? And you can actually calculate the Kb of that, because this would have a Kb, and I'll show you that here in a minute, how to do that. And so you don't really have to memorize this chart, or I don't have to give it to you, which tells you which species produce neutral anions or cations. Mostly here, these are all acids. And so here you see the strong acids here: nitric acid, sulfuric acid, hydrochloric acid, of course perchloric acid, which is always missing here for some reason. HClO4 is also strong. It will produce pH neutral anions because they will not go back and produce these acids here, so that's why. Whereas all of the weaker acids will produce weak bases, right? So the anion will again, phosphoric acid, which in the first ion dissociation will produce dihydrogen phosphate, produces a conjugate base that is actually going to act as a base and react with water. And then, yeah, so that's basically the idea. So here are those acids: hydrochloric acid. Oh, there's perchloric acid. Okay, it is there. And also remember, sulfuric acid is polyprotic, so it's only that first hydrogen that is strong. The second hydrogen is actually weak, so that's listed here, right? So that's the second ion dissociation. So the sulfate ion actually will act as a base, but the hydrogen sulfate will not. the hydrogen sulfate is here. That's pH neutral. But the second dissociation, I'll write it real quick, that HSO4 minus, which will react with water, will produce sulfate and hydronium. And then, of course, this here, this is -2, is a conjugate base, and it will react with water to form a little bit of hydroxide. And so that is going to have a pH that is larger than 7. All right, so for example here, this is where I show you how to find the Kb of these weak salts, right? So find the pH of a 0.100 molar solution of sodium formate. Okay, formate's not something that we've learned about as a polyatomic ion, but if you look at a chart, and I've got this one here truncated so you can find formic acid, but you basically just need to find that conjugate base. If it's not on there, it's probably comes from a strong acid and it's pH neutral. But this one is not. If you find it, okay, so this is formic acid. So this compound here is sodium formate. Told you already that the sodium is nothing to worry about, but it's the formate that is going to react in the reaction shown here to form some hydroxide, which will produce a pH larger than 7. So it's going to be a basic solution. And so you can look up the Ka for that. And so this relationship here, the Ka times the Kw, the Ka times the Kb equals the Kw, that's convenient. This is how the formate and the formic acid are related. And so if you take the Kb and you divide it, you divide the Kw here, this is Kw, divided by Ka, you get a value for the Kb, and now we can actually work this problem. We can set up an ice table. We can say that we had a 0.100 molar solution of formate. Why do we have that? Why does that not shift? Well, because sodium formate is a soluble ionic solid. There's no equilibrium here. Everything's going to break into sodium and formate. So we have 0.100. If we had a liter, we would have 0.100 moles of formate here in solution. So that's why this is liquid here, so it's irrelevant. We're going to leave that blank. Shouldn't even be listed in an ice table. But initially we don't have any of that and no hydroxide. Yes, we have some hydroxide from the autoionization, but that's irrelevant. So that's just our regular ice table. Then it's going to go down by x. It's going to go up by x, and so at equilibrium we have 0.00 minus x, x and x. We already determined Kb, so I can plug that straight into the equilibrium constant formula. 5.56 times 10 to the minus 11 equals x squared divided by 0.100 minus x. I'm going to make my assumption, as always, that x is very small. Good assumption, right? We have 0.1 molar and 0.1 molar solution, which is not high, but it's not low either. Anyway, we're going to make this assumption and then test it, that x is equal to 0. So then x would be equal to the square root of 5.56 times 10 to the minus 11 times 0.100, which is equal to 2.4 times 10 to the minus 6. Of course, that's the hydroxide ion concentration. So if I can calculate the pOH, and there you can of course get to the hydronium ion concentration differently, but I'm going to work it this way. So the pOH is going to be equal to the negative log of 2.4 times 10 to the minus 6, which gives me a pOH of 5.62. And if I want to know what the pH is, I just do 14 minus 5.62, which gives me a pH of 8.38. And it's important that you think about the value too, right? This should have a pH that's larger than 7, because that implies that we have a basic solution. We know this is basic because formate is a conjugate base. This is just for you to look at. This is how I determined the Kb for this particular reaction, or that conjugate base here, the formate. And it doesn't matter what I have here. It could be potassium formate. It would be the exact same concentration. It would be the exact same Kb. It has nothing to do with the counter ion. Here's everything worked out. Oh, I forgot to do the test, but here's your test. We took X, divided it by the original concentration times 100, and we got something that's way less than 5%. Now, they work out the pH a little differently. They calculate, they don't go to the pOH, they simply calculate the hydronium ion concentration with this equation here, the Kw equals the hydronium ion concentration times hydroxide. That's fine, and then you take the negative log of the hydronium ion concentration, and you end up with a pH of 8.38, which is the same thing that I had. So here's a chart of weak acids that you will be given, and I'm also going to give you this formula here. You just need to make the connection, right? So if I give you some sort of salt, I'm just going to use what we had before, potassium nitrate. And if you don't remember, that nitrate is pH neutral because it comes from nitric acid. You look at this chart and you try to find, there's nitrite, that's different, fluorite, formate, benzoate, acetate, chlorate, cyanide, something phenolate, don't actually know, doesn't matter, it's not on there, so that's going to be pH neutral. But any of the other ones here, that's what you do. If I gave you benzoic acid or sodium benzoate or something, calcium benzoate, potassium benzoate, strontium benzoate, right? C7H5O2-, you go find it on this chart. If you find it, then you can set up the reaction, right? I'm just gonna call that BA, okay? This is gonna be called BA. I can't think of anything better. So then we know that BA is gonna react with water to form HBA, and then I have no room here, and then hydroxide. So that's going to be the same thing over and over. That's your reaction. That has a Kb. That Kb can be calculated with this up there. All right.